The slope of a line. The slope is typically denoted with a lowercase m. For a linear equation or a line, it measures the steepness of a line. The slope is constant in that at every single point on the line is changing at the exact same rate, so it has the exact same slope. However, for nonlinear equations, or an equation where the graph has a curve, the slope is constantly changing. Every single point, the graph is changing at a different rate, so the slope is different. So since we're working with linear equations, let's go back and look at the four possible graphs of a line. We said a line can either increase, decrease, be a horizontal line, or a vertical line. The slope would tell us what type of graph it is as well. If a slope is positive, we know that line is going to increase. If the slope is negative, the line will decrease. Horizontal lines do not increase or decrease, so the slope is 0. And vertical lines do not have a slope. The slope is undefined. So we're going to be talking and working with slope a lot for the remainder of this chapter in multiple different ways. One way we're going to be working with the slope is to find the slope of a line given 2 points. In order to do that, you have to know the formula. The slope will be equal to y2 minus y1 over x2 minus x1. So once again, we're trying to find the slope of a line given 2 points. So if we have 2 points, that means we have two ordered pairs, an x and a y in the first point and x and y in the second point. So to keep these two x's and two y's separated, we're going to call x sub 1 the x coordinate from the first point and y sub 1. Same thing for the second point, x sub 2 and y sub 2. Just once again to distinguish between those two x's and those two y's. So to find the slope of a line that passes through these 2 points, we just substitute those values into the given formula here and simplify. So example 1, find the slope of the line passing through the given points. 3, 7, 0, 2. So I'm going to write right out on my paper what the values for x2, y2, x1, y1 are. Then it's just a matter of substituting those values into the formula. y2 minus y1, 2 minus 7, all over x2 minus x1, 0 minus 3. Simplify. Negative 5 over a negative 3 simplifies to a positive 5/3. So right away, the fact that that slope is positive, we know that the line passing through those 2 points will be an increasing line. Example 2, negative 5, 0, x1, y1, negative 1, negative 6, x2, y2. Substitute those values into the formula. y2 minus y1, negative 6 minus 0, all over x2 minus x1, negative 1 minus a negative 5. So the numerator, negative 6, the denominator, negative 1 minus a negative 5 becomes negative 1 plus 5, or 4, which then simplifies to negative 3 halves. Example 3, the points 2, 0, 2, 9. So x1, y1, x2, y2, substitute them into the formula. y2 minus y1, 9 minus 0, over x2 minus x1, 2 minus 2. Simplify. 9 over 0, of course a fraction, can't have a 0 in the denominator, which means it's undefined. So the type of line that has a slope is undefined is vertical. This would be a vertical line passing through these 2 points. Now that we know what the slope is, we know what intercepts are, it brings us to another form of writing a linear equation with 2 variables. It's called the slope-intercept form, which is the most common form. So from this point forward, if the linear equation we're working with is not in slope-intercept form, the first thing we're going to do is get it into this form. Y is equal to mx plus b, where m stands for the slope of the equation, and b tells you where that y-intercept is. Be at the point 0b. So just from looking at an equation in this form, we can derive a lot of information about it, the slope, and already one solution or one point that it passes through, the y-intercept. An example of an equation in slope-intercept form, example 4, y is equal to 5x plus 3. So the slope is simply equal to 5. B is equal to 3, so therefore the y-intercept is at the point 0, 3. Graphing an equation is much easier in this form. Well, we already have one point that the line passes through, the y-intercept 0, 3. So we only need to find one more point, and the slope will tell us where to go in order to find that next point. Now typically we like the slope written as a fraction at this point, so if it's not a fraction you can just put a 1 under it. And we use the saying rise over run, where the numerator of the slope tells us whether we go up or down, the rise. If it's positive we go up, if it's negative we go down. The denominator of the slope tells us we go left or right. If it's positive we go right, if it's negative we go left. So in this particular case, a positive 5 over a positive 1 means from our y-intercept we go up 5 units and to the right 1 unit. It gives us another point that the line passes through, so all we have to do is sketch that line in order to come up with a graph of that equation. Example 5, linear equation in slope-intercept form. The slope negative 1/3. B is equal to negative 1, which makes the y-intercept the point 0, negative 1. So to graph that equation, the y-intercept 0, negative 1. The slope negative 1/3. We typically move that negative up to the numerator, but technically it doesn't matter. We could move it down to the denominator, as we'll see here in a minute. If we move it up to the numerator, negative 1 over 3 means our rise is a negative 1. We go down 1 unit. The run is a positive 3, so we go to the right 1 unit. If we would have used or moved that negative down to the denominator, we would have gone up 1 unit and to the left 3 units, which, as you can see, gives us the exact same line, showing you it does not matter where you move that negative. But the slope is decreasing because the slope was negative in that equation. Example 6, still a linear equation in slope-intercept form. Slope is equal to 7, b is though equal to 0. B is not shown, so obviously it's just plus 0 or 0, which makes the y-intercept at the point 0, 0, or the origin. So to graph it, begin with the y-intercept, the slope, we can write it as a fraction. Positive 7 over positive 1 means we go up 7 to the right 1. Sketching the line passing through those points, an increasing line, what we expected because the slope was positive. And example 7, a linear equation with 2 variables, but we notice in this case it's not in slope-intercept form. It's that standard form, which really didn't tell us a whole lot about the graph, other than the fact we know it's going to be increasing or decreasing, but that's about it. So what we want to do is begin by putting it into slope-intercept form. Subtract 8x from both sides, so negative 6y is equal to negative 8x plus 12, and then divide everything by a negative 6. So y is equal to positive 4/3 x minus 2. Now we did not change the value of that equation, all we did was change its appearance. Just by putting it in this different form, slope-intercept form, we know a lot more about the equation. We know the slope is a positive 4/3, so we know it's going to increase. We know the y-intercept is down here at 0, negative 2, and we can quickly graph it. From the y-intercept we go up 4 units to the right 3 units. So like I said, much more useful slope-intercept form. So if an equation is not in slope-intercept form, the first thing we're going to do is get it in the slope-intercept form. Even when we're asked to write an equation for a line, we're still going to be using this slope-intercept form, y is equal to mx plus b, where the only difference between one equation, linear equation in slope-intercept form, and the next are the values for m and b. So as long as we're able to find m, the slope, and b, where the y-intercept is, we can just plug them into the formula and have an equation. Now in this case, we're simply told the slope, negative 4, so m is equal to negative 4. We're given the y-intercept, the point 0, negative 5, so b is simply equal to negative 5. So substitute those values into a slope-intercept form equation, which gives us y is equal to negative 4x minus 5, a linear equation with slope negative 4 and y-intercept negative 5.